Welcome to tonight's general statistics lecture. We're going to do tonight's session in a couple of different parts. First, we're going to start out going over the material in chapter 4, the average and standard deviation. Before we get into today's overview of the material, we're going to do a brief overview of the primary takeaway topics from this chapter, then do the review exercises, and then if we have time, we'll work on some exam review questions for the upcoming exam that cover some questions that cover material we've already covered. So I've laid out a few items and we can go over those if we have some time. I'll also plan to stay after lecture tonight for an office hour here in Blue Jeans. So if you have remaining questions or things you want to discuss, feel free to stay after lecture and we can go over additional problems then. Usually office hours for statistics are just that, doing problems. So that's what I'm expecting when I schedule an office hour online or in person, but I like to do virtual office hours, and when you see them pop up, those are just opportunities to come in and practice problems. First, let's talk a little bit about some tips for studying effectively and efficiently this material, and especially this semester, because in this spring semester, you have a really compressed time frame. And trust me when I tell you, I've cut a lot of material, even compared to a normal semester, has even more than this on this first exam. So we've really honed it down because this timeline is so compressed. So I understand that means that it takes, I understand how hard that is, because I know already that learning statistics is like learning a new language. And I don't use the metaphor lightly. It truly is like learning a new language, because when you're learning statistics, you're learning a whole new way of thinking, and you're not just ready to do it right out of the box. You first got to learn the alphabet. You've got to learn some basic vocabulary. As you go, you have to keep learning new vocabulary, more complex rules. You've got to learn basic rules of grammar. And so that's what we're doing right now. You're learning that kind of boring stuff, the less exciting parts of learning a language. The alphabet, which for us, I would say, were the basic things about experimental design and just variable types and things. These really discrete topics that then we're going to layer into material that's more exciting in a lot of ways, in ways that you'll be able to see more directly, interesting ways to apply it in your own work and school activities in the future. So we are going somewhere with all of this, but because of our compressed time frame, I've tried to get these basic bricks in the wall early. These these are all early, and we haven't had as much time to look at some of the other applications. Hopefully you're seeing some applications that are interesting in the lab, and in labs, that's what we're really going to be working on, is taking the stuff that we're doing in our lecture material and applying it in interesting contexts and ways that you can use fluidly, hopefully, in your daily lives. And that's why labs are a big portion of your grade, 28% exactly. But that doesn't mean that you should spend an inordinate amount of too much time on the lab. I'm estimating that the labs, again, should average maybe 2 or 3 hours tops, even including watching the lectures. A lot of people do work on their parts of their lab while watching the lab lecture. And I think that's a great idea. So if you're struggling in any area in particularly with doing a lab report, with exercises, don't let statistics do a number on you. Don't fall into the rabbit hole of statistics study time. Please reach out to me. Please call or text, and I will help you out with the problems. I actually like doing these problems, and I'll be very happy to help you. I will not judge you for asking a question, except with maybe a positive judgment, because I love to be asked stats questions. And I know that students who do well are students who do ask questions, who start asking questions early and then ask a lot of questions. So that's my tip to you. Start asking questions. Ask questions of me. I'm opening up a discussion board tonight where you can post questions about the exercises by exercise, and it's explained online. And try to limit your time. So think about the exercise sets as a learning opportunity. I'm not expecting you're going to get all of these the first time out, or that you're going to, the exercise sets are to help you reflect on and build on what they're talking about, and to recognize where maybe the previous preconceived way of thinking about data that you've come in with, the exercise help us address some of those misconceptions that people come in with. So don't worry too much about them. Just try your best and make sure to look at the solutions to see how you're doing. But just turn in for your answers your honest effort. You don't need to correct them. That's why they're graded complete, incomplete. Okay, so hopefully that will help you shake down some time. And really, if you've been working on any problem for a long time, I'd say 5-10 minutes, that's enough time. Then it's time to reach out for help. Okay, one final thing that I want to discuss with you before we jump into this thrilling material on averages and standard deviations is that I know statistics can be, it's emotionally hard, and it's emotionally hard in a semester where students do this material in twice as long. So it's especially hard in this compressed semester. And so knowing that, you can let's try to proactively manage that anxiety. And we're going to talk about a couple of different strategies in the next week or two to help with that very problem. One of them that'll be in the lab this week is power posing. A couple of you who called me have already heard about power posing, because I think it's a very effective strategy. If you're curious, there's already a folder in your lab 2 week with some links to the power posing, or maybe it's in course content. Anyway, but today's topic that I want to share to help you manage some of the common difficulties is another one called a power song that I've found in previous semesters. Stat students find it, so it can be, even I find this, stat students, heck, I have trouble getting activated to do this stuff. I was sad no one was calling me, so I went to my for help with their stats. And so I went to my power song to help me get energized to do statistics. So for me, I have embraced, as of late, the Moana soundtrack. I really love Moana. It's very empowering. She crosses an ocean, and it really exceeds other Disney movies on a lot of measures, which we will actually look at some of the content analysis research of Disney movies. But Moana is fantastic. The music is very inspiring, so it helps inspire me to get activated. Now, when you find a power song or a couple of power songs, I think that some of the other best ones are ones that are funny or, either inspiring or funny. For example, another student last semester said when she got started doing the exercises, she would feel like some sad Whitney Houston song. But by the end, as she was getting the material, she'd move on to feeling bad, like Michael Jackson, bad in a good way. And this can be very effective. It can help you get the music, listening to that song can help cue your mind. If you consistently pair one or two power songs with your getting started doing stats, then when you need to get yourself activated more quickly, if you listen to your power song, it can help you get in the right mood. And so try it. It does seem to work. Now, I'm not suggesting listening to music while doing stats necessarily. I don't find that helpful, but to get activated and during breaks to get re-energized, it really is helpful. So that's today's surviving statistics study tip. Our first topic for today's lecture over the material is measures of central tendency. This is the average or mean, median, and mode. And I've just grouped these. I'm adding in some additional ways of framing and thinking about these. I know your book doesn't use the measure of central tendency category for these, but I like to put things into useful groups when we're going to use them later in significant ways. So we'll refer to measures of central tendency as a group later for different applications. So this is part of previewing for some effective longer term study. Measures of central tendency give you the idea of where the center of your data tends to be. And we'll talk about each of these in a little bit of detail, the average in the most detail. And the median and the mode just a little bit. The mode is the most simplistic measure of central tendency. It only applies when you have nominal, well, you could get a mode of any type of data, but when you have nominal data, the only measure of central tendency that's appropriate is the mode. However, if you have data that's more where there's a rank inherent in the data, so ordinal data or interval data, then you can use the median. And depending on your data set, if you have interval data, that will help you decide whether to use the median or the mean. And we're going to go over how to make these decisions in the future. I'm just layering in why these matter to us in future lectures. The average is our first measure of central tendency. The average of a list of these kind of. So the average of a list of numbers is simply their sum divided by how many there are. And I'm sure that you have all found an average before at some point in your lives. When we calculate the average, first as listed here, we sum the numbers and then divide by how many there are. So if we look at this example, which is from chapter 4, exercise set A, number 3, you've got two lists of numbers and you're asked which has the bigger average. or are they the same? And it says to try to answer without doing any arithmetic. So let's first try to eyeball it like they say. Well, when I eyeball this number 1 here, I can see that the range of scores is from a low of 3 to a high of 10. So that is a bigger range than the scores over here. Also, the n, which is the how many there are, n is our shorthand for the number of subjects or the number of cases. We can see there are 6 in this first data set, but 7 in the second one. And since I'm looking at these two aspects, the range and their n, and I'm going to guess that the list 2 has a bigger average because the numbers are the same. The first 6 numbers are the same in list 1 and list 2, but list 2 also has an 11 in it. It has one additional number. It's a high number, so it's going to pull that average up to it'll pull the average up as well. So which list has a bigger average? 2. Now, if we wanted to do the math here, which we don't, you don't have to, but just to give you an example here, the average, your book's kind of light on using the formulaic symbols, but I will use some of them because some of these are in standard use and you should be aware of them. This one is the average, aka the mean. You'll hear me say the mean or use the term mean for average frequently because I'm just used to using that term. So this is our average. This symbol here means sum. This is an equal sign. I'm sure you know that. I don't actually want it there now, but because I want to show you some of these other terms. N is the number of cases. And we might use tot or total to give the end result of a formula for average that looks like X bar. And this is how you say, I'm sorry, I left that out. You say this symbol, X bar. I'm going to try to say mean, but if I do forget and I say X bar, this is what I'm talking about. The X with a bar on top. It's the mean. X bar is equal to the sum of scores. X is an individual, sum of X over N. X is an individual score. Oh. Okay. And so what would that look like for one of these? It would mean adding, 10 plus 7 plus 8 plus 3 plus 5 and finally plus 9. The sum of these, right, divided by Rn, which is 6. So that's just a mathematical breakdown. Some people find it helpful to see things in the symbolic format like that. Next, let's jump back for a minute and talk about these other measures of central tendency briefly, although we won't use them as much as the mean. We will use them occasionally. The median is simply the point at which 50% of the scores are below and 50% of the scores are above. and the mode is the most common score. And we're going to apply these in a couple of examples briefly. Here we have a histogram for this list of data with the points 1, 2, 2, and 3. So there's only an N of 4. Right. And they're saying this histogram is symmetric around 2. The average. 2 is the average. And 50% of the area is to the left of 2 and 50% is to the right, which makes 2 the median as well. So we know that the mean equals 2 and the median equals 2, right? You can see hopefully how this is the spot where 50% of the data is above and 50% is below. And also we can find the mode for this data set too, the mode being the most frequent score. What's the most frequent score? 2. And to preview a bit into chapter 5, when a distribution has a mean, a median, and a mode that are all the same number, we say that distribution is normal. And we are going to unpack that term more in the latter part of our lecture. Here we have a histogram for the weights of, before we look at the skew on this one, I actually want to look at this general overview of skew in the tails of a histogram. And so these are histograms where the curves have been smooth. So a histogram where all of the bars are visualized separately would look like figure 4 here. But we often see them in practice smoothed like they are in this figure. And there are 3 primary types of histograms that we'll talk about a lot. We'll especially talk about this one in the middle. That's symmetric, and the average is about the same as the median. This, with some other qualities as well, will come to be a normal curve. So a normal curve has these qualities. Sometimes we have a curve that has a skew though, and this is what we call the long right-hand tail and the long left-hand tail. These extended tails. The extended tails are skew. And we classify skew in these based on the tail. So first, let's think about a long right-hand tail. A long right-hand tail is what you see in this example here, where about the histogram for weights of the women in the N. Haynes sample. And you can see that the tail goes off into the right here because generally women's weights were grouped around the central area here between about 210 pounds and 110 pounds or so, approximately. But then when you get beyond that, you can see that there's these people, these outliers who have much, much higher weights. And so they skew the distribution by pulling the tail to the right. And so we classify or we name these based on the direction of the skew. This is the direction of the skew. So this is where's my, a positive skew is the long right-hand tail. That's because we call this the positive side of the distribution. This is the negative side of the distribution, as you start to learn about in Chapter 5 related to the normal approximation for data. So very simply, we label our skew based on the direction of the tail. So it's a positive skew. Any thoughts about what this might be? This long left-hand tail? I'm giving away the answer here. Somebody jump in. It's a negative skew. So just like we called this first one a positive skew because the skew is in the direction of the tail, we call the negative skew the situation where we have a long left-hand tail. Now, as students, and I am expecting people to respond out there in the chat, and if you're watching this video, think about this yourself. Imagine you're a student in a stats class. Shouldn't be hard. Which distribution would you rather have for final grades? Would you rather have a positive skew like on the left here where these are percentage grades starting at 0% to 100%. Symmetric distribution, again, from 0% to 100. Or a distribution with a long left-hand tail where the skew is negative. You tell me, what kind of grade distribution do you want? I have all night, people. What kind of grade distribution do you want? A positive skew? You want this distribution on the right here where most people get below 50%? Do you want a distribution where most people get around 50%, give or take a little bit, or a distribution where most people get above a 50%?
You'd want to be above 50%.
Yes, thank you for talking.
I had my audio off. I kept talking.
No, thank you for pointing this out. The chat wasn't repopulating in my window, so I closed it and reopened it. So thank you, everybody. I can see you all do want a negative skew. I'm happy to see that. The chat just wasn't updating. You should watch the Moana movie. It's worth taking a break from stats to watch Moana and get yourself an inspired vision for for crossing the ocean of statistics. So thank you for alerting me to your answers. Yeah. We, of course, want a negative skew in the distribution, and I will tell you what. That is what grades usually look like, okay? So if you're scared about the class, well, this is what the grades usually look like. Most people get an A or a B. Some people get lower scores, but but people who do all the work generally get an A or a B. Some might get a high C, but really it's a heavily skewed distribution. So don't lose hope. Just keep working. I've proactively set up the distribution and the grading, so it will work out like this. Okay, I promise. And I always keep my promises to students. Okay, one more histogram. So now we have this histogram with the data from the N. Haynes sample. And I want to point out one, I guess we should maybe look at it in this one. So one final point about the histogram and how skew affects our thinking on these. And if you're not, like, please turn off your audio when you're not talking, because we can all hear the background noise. Thanks. So it's always shocking to me how sensitive these microphones are. So here we have these 3 histograms back, and we talked about this first scenario where we have a symmetric distribution, and then the mean, the median, and the mode are all the same. They're all the same. They're right here, approximately. But when we have a skew, we have a different scenario where the mean is always pulled in the direction of the skew. The mean, that is relative to the median, okay? And this is an important thing to remember. So for example, we can see, starting here on the positively skewed diagram, we could see we'd get to, well, the mode is going to be right about here. This is the most common score. But 50% of the distribution is going to then fall around in here. But because of these extreme scores, the mean is going to be pulled even further away from the mode. And it would follow the opposite pattern when we have negative skew. We still have the mode up here. The most common score is always, these diagrams always go score by frequency on the y-axis. And then again, the median is going to be in approximately this area. And the mean is going to be pulled down by the skew, always in the direction of the tail. Okay. And that's what we can see happens in this histogram. So we could figure these percents per pound, because this diagram has intervals of 10 pounds per interval, although it's a little tricky to know exactly what the percentages are at each of these points. But if we did, we could just take the percentage and multiply by 10, and then sum the percentages until we get to 50%. And if that seemed a little confusing, don't worry. I'm just layering in ideas as we go. You're not going to get everything first time around. That's why I try to introduce topics early on and then keep layering them back in. So that was the
Can
average.
I talk to you after?
Absolutely.
Can I talk to you after class?
Yes, I'm planning to stay for an office hour after our lecture session. So, yep, I'll be here.
Okay. All right.
Okay. So Next, we're going to talk about measures of variability. And measures of variability are an umbrella term that includes the standard deviation, the range, the root mean square, and the variance, which I don't think they've introduced yet. So this is an umbrella term that helps us get an idea of the distribution of scores around the mean. We know that the mean tells us as long as our scores are distributed symmetrically, the mean tells us about where the middle is of the distribution, and the measures of variability give us some different ways of conceptualizing the spread of scores around the center. And this is this is an Einstein quote. This should guide our thinking of approaching the exercises, not to I hate that phrase, beat a dead horse, but I can't think of something better. But remember, you're not going to get everything the first time around. You're going to get to the good ideas, those eureka moments, by getting lots of ideas, by trying lots of exercises, and then just throw the bad ones away. And then poof, oh, now it makes sense. Oh, whoops. So the standard deviation, I don't know what happened to that. There was a picture there. Well, we'll just grab it again. So the standard deviation gives us a way to measure the spread of scores around the mean, and also to scale them in a way that gives us a standard way to talk about how far scores tend to be from the mean. The standard deviation is an important topic. We're going to get to the standard deviation vis-a-vis discussing the root mean square. The standard deviation has, so the first step in thinking about the standard deviation, which we'll unpack in a little more detail in a moment, is to think about the root mean square. The RMS size of any list of data is simply the square root of the average of each entry squared. So that is to say, we would take here we have an example of the average. You can see how here we have the average, and it fits in with our way of thinking about the average already. We've got our mean equal to, here we have the sum of all the scores divided by the number of scores, 5. Now, if we get the average, neglecting the signs, because when we get the average, it gives us a center, but when we want to figure out how scores are distributed around that center, we need to consider scores that are above the mean and scores that are below the mean. And so if we simply summed our scores and didn't pay attention to the signs, then we wouldn't be able to get an accurate idea of how far above or below the mean scores tended to be, because the average of all mean deviations, or the average of all deviations from the mean, is 0. So we have by deviation from the mean, that's just the score x minus the mean x bar. So in this case, we would take, we have each of these scores. And then minus the mean. We already know the mean is 0.2. And then we would get for each score their deviation from the mean. And I see when I wrote this list, I forgot the signs at first, but you see I added them in here. So these are our scores. And you get the deviation from the mean for each individual score, just like that. There's this x minus x bar. This is a calculation we'll use really frequently in a lot of different problems as we move forward, or in different types of tests and measurements. So that's why I'm introducing it here along with this other stuff. And when we get to the exercises, I will show you how to do these in Excel as well. So if you're wondering about that, don't fret, it's coming. So this is one option to get the deviation from the mean, but there are issues with that theoretically in terms of or mathematically. And some of this is just explanatory. What I want you to take away is an understanding of the RMS and the standard deviation, but you don't necessarily have to be able to mathematically, prove all of this. I'm just providing you with context to help it make sense. And that's what they're doing in the book too. So if we get the average neglecting signs, you can see they took the absolute value, which again we'll use later, of any score is that score with the sign dropped. So the absolute value of -8 is 8. So what we have here, the average neglecting the signs, then is 4.6. And the reason we would want to take the average neglecting the signs is that, or the reason one would even think about this when proving this topic, is that there's a problem with scores above and below the mean. So we have to figure out some way to account for that issue of there being scores above and below the mean. Just go with me on this. And so we can do that by dropping the signs, but another way to do it, and a way that is better mathematically, is to square the number, like we do here in the RMS calculation. When you square the number, it automatically drops the sign. So a negative number squared it becomes a positive number. So then all these numbers are positive, and it's, for a variety of reasons we really don't have time to get into, mathematically more reliable. This is a better way to handle the problem, just to sum it up, is to square the numbers. So that's why we do it. We square each number and then sum them, divide by the number of cases, because the number of cases is always relevant when you're thinking about the spread of scores on a distribution. We're going to talk about number of cases a lot. So it's no surprise that we see number of cases in the denominator here. We're going to see number of cases in the denominator again in tons of calculations going forward. Are going to have a similar basic structure to this one, where there's a way to account for a number of cases in the denominator, and in the numerator we look at variance or variability in the data. And so after we get all these squared scores and then sum them, we need to finally take the square root, because even though squaring the numbers was a good way mathematically to deal with the signs, we need to get the numbers back into the same scale that they were in the original data set. And so in order to do that, we have to unsquare or to unsquare the square we did, as in take the square root of our squared scores, okay? And we end up here with a root mean square of 5.4. And are there questions out there about the calculating the RMS? Okay, that's great. So,
well, I have lots of questions, but that's why I'm saving it for afterwards.
Okay. No, you can't just go ahead, Stephen, and make the number positive. You have to square the number. In order for this calculation to come out right, there are no shortcuts. Let me just give you a heads up here for everything in the future. If there was a shorter way to do it, I'd be teaching you that way. So there's no like way you can circumvent steps of anything we do, because for reasons that we don't have time to get into, you have to square them and then unsquare them. Yeah, the number will be positive after you square it, but it's a whole different number then. So to look at this step by step here, the calculation here, if we square 0 squared is still 0, 5 squared is 25, 8 squared is 64, 7 squared is 49, and -3 squared is 9. I mean, if you mean in terms of the squaring, does it matter if you have the positive? Well, like I said, it doesn't matter, but you should still, if you're thinking, well, you could save time by not writing a negative sign, trust me, that's not a good idea. I always suggest people write out the whole calculation, actually, because it doesn't, when you start trying to skip steps in your writing, you just end up with wrong answers. Even me. Well, sure, since 5 and -5 squared, but you still, if you're doing this problem, you write it out in this exact same format like they did. Write the item, and if it's a negative, include the negative. Because let's say, here's why. Let's say you don't get the right answer. Well, you want to be able to go back and look at what you did earlier. And if you were dropping the signs, you may or may not have got the numbers right, especially if you're transferring over multiple numbers. What if there's, an 8 in the data set and a -8 in the data set? Again, if you're dealing with more than 5 data points, it's tricky. Trust me, just we're squaring it for a reason. Also, as you'll see in the future, the signs will matter quite significantly when we get into the normal distribution and dealing with standardizing the normal distribution. So it's good to get used to them. But that's a great question, and I'm really glad you asked, because I'm sure other people out there were thinking the same thing. And so the next step in this problem would be to get your divide by 5, and then you would finally take your square root. But again, if you're rewriting a problem, don't try to skimp and say, well, in this step, I'm only going to do this part, so I won't put the radical, write the radical on there. I mean, you're talking about things that would cost you a second of writing here or there, and trust me, it doesn't pay dividends in terms of your long-term study plan, because it's easy to drop a radical or to lose it when you get into, as we will later, tests that have multi-step calculations where you really do have to keep track of this stuff. And so we build from the root mean square. which is a slightly better way of measuring than the average neglecting signs. And as you could see, if you just drop the sign, you don't get the same number as you do if you compute the root mean square. So that's one final reason why we can't just drop the sign, because you end up with a different number. Okay. Next, we're going to think about getting the spread of the data, right? So the spread is in the standard deviation, and the standard deviation tells us how far away the numbers on a list are from their average. The standard deviation we will discuss in almost every single topic we do for the foreseeable future. We will always have a standard deviation to accompany other measurements. Or not always, but almost always, I'll say. So that is to say, expect to see more of this. It'll make more and more sense as we keep doing standard deviations. That doesn't mean I want you to spend 6 hours studying this, part of the chapter. I just want you to know you're going to get more opportunities to learn it better and better. And so one important point about the standard deviation is that most scores fall within plus or minus 3 standard deviations from the mean. So that another way to think of this is that most scores are, an entire distribution of scores is generally within 6 standard deviations. And the standard deviation is also quite useful because it helps us to have a standardized measure for spread so that you can compare standard deviations from different studies. A standard deviation is always, one standard deviation from the mean is always 34% of the population. This is just a moment. As you can see in this figure, this is a common bit of knowledge that everyone has to leave a stats class knowing this over here. So within one standard deviation from the mean, you have 34%, or above and below, one standard deviation above and below the mean is 68%. So here we have our average. And if I was to draw a normal curve on here, this is not a great normal curve, but close enough, because I'm trying to, and I know some of this wasn't in chapter 4, I'm layering in some material from chapter 5 to help us get through that a little more quickly when we get there. So you can see this is a normal curve, or imagine it is, and here's the mean, and one standard deviation from the mean is always 34% of the distribution. Underneath this whole curve, this whole thing is always, that's misleading, 100%. So you have under this curve 100%, or a proportion of 1. There's one whole data set under here. And so 34% of that data set falls within one standard deviation above the mean, and 34% is one standard deviation below, for a total of 68% above and below the mean. When we look at two standard deviations from the mean, we know that 95% of the distribution is going to fall within two standard deviations above and below the mean. So that's two standard deviations to the right and two standard deviations to the left, or two standard deviations in the positive direction and two standard deviations in the negative direction. Okay, and we will look at different ways that we can use the idea of standardizing the data set to help us break up the distribution and come up with useful things like percentiles and standard scores so that we can compare across studies and different distributions. And to compute the standard deviation, it's similar to the root mean square. We would say it's the root mean square deviation from average. So this is where the idea of the mean deviation comes in. So instead of just getting the root mean square of the scores themselves, we're going to get the root mean square of the deviations. Here we can look through this example, finding the standard deviation of this short list of scores with scores of 10, 20, 10, 15, and 15. First, we have to find the average in order to get the standard deviation, because the standard deviation, the average, is part of the calculation of the standard deviation. We all remember how to get an average. And here it is laid out for us. So we know the average is 15. Why am I rewriting terms over here when we have them already on the page? And I'm actually going to write them on the left side. Why? Because as we move forward, like I previewed earlier, we're going to have increasingly complex calculations that we're dealing with, and scenarios where we have lots more terms, and you're going to need to keep track of the terms. And it is most efficient to get yourself in the habit of keeping track of important terms like that in a list on the left. I'm going to present you with a specific and observationally tested method for effectively organizing these more complicated tests we're going to do. And part of my method includes keeping track of your terms in a list on the left. Okay. So I'm doing this to help layer in some good habits for us for the future. So our next step is to just get the deviations from the average, just like we specified before. And I put my terms over here. And we'll put our analysis over here. Don't be scared by the word analysis. That's just our calculations. But this is statistics, so we're going to call it our analysis. First, we're going to get the mean deviation. And to do that, we're just going to take each score minus the mean. And we only have these 4 scores, so we have 20 minus 15, 10 minus 15, 15 minus 15, and 15 minus 15 again. What does that equal? Well, 5, -5, 0, and 0. And we could make a little table of our deviations from the mean. That's an effective way to keep track of this. And we'll make tables like this to keep track of our data in the future too. Sorry, I wrote this a little bit over the problem. So this is the mean deviation here. And now that we have these numbers, we can use them to get the RMS size of the deviations. And the RMS size is just the root mean square. So we're going to square and get then the root at the mean, or get the root, square root, vis-a-vis the mean, more or less. I can't really break this down for you mathematically. We just don't have time. And you probably wouldn't find it as interesting as other things we could do. But just to be clear, this is very similar to our last calculation. We square each number, each deviation first, sum them, and then divide by n, the number of scores. And over here, if we were doing this problem from scratch, we would want to have our n listed. So we would have that quickly for future computations. We do that. Then finally, once we have this ratio of the amount scores deviated from the mean by the average score, we get the square root of that, those squared scores. And here we have the standard deviation. And the standard deviation is in the same units as the data in the problem. Okay, so there you have it, folks. That's the computation, and we're going to breeze through these exercises here. I have laid out all the exercises in chapter 4, and I'm thinking we can get through them quickly. I also have chapter 5 ready too, but I'm thinking that the most effective way to manage this week's material is to do this chapter 4 material today, some exam review. Then I have, as you, most of you probably already know, I have another section of this class that meets on Wednesdays, and they are attending your the Tuesday night lectures, and you will be welcome to attend their Wednesday night lecture tomorrow afternoon. I guess it's at 4 to 7. But it'll also be recorded and available for you to review, wherein I'll go over chapter 5. And then on Thursday, we'll do chapter 6 and then some exam review. All right. And just as they received a link to attend this lecture, I'll post a link tomorrow so that you can attend their lecture if you like, or again, watch the video. It'll be posted in the media gallery. Okay. Yes, chapter 5 is a very important chapter. We will review chapter 5 as well on Thursday. I won't neglect it completely, but they will have time for a more extended discussion of it in the Wednesday night lecture, just because we only have so much time. You know, you think about this, we would normally spend twice as much time on this material. So yeah, try to make it tomorrow if you can. I can answer questions for you this evening about chapter 5 after lecture. That'd be fine too, but I'm sure tomorrow night's lecture will be very helpful. Chapter 5 is a topic that I know I keep saying we're going to see this more and more, but chapter 5 is pretty important. I'll just leave it at that. or important in the sense that it's usually one that people find kind of tricky getting the hang of. Okay, so next up we are going to do these exercises for chapter 4. And just like this little baby deer is being helped to walk by her mommy doe, I'm, through doing these exercises with you, helping you to get your statistics legs working. And I know you're just learning to walk. So, whoops, back to the cute thing. There we go. So ask your questions. Remember, I'm looking for those questions. If you have a question, I guarantee other people do too. And so don't be afraid to ask. So first we're going to do this first problem, and I'm going to take the opportunity to show you how to get the average and standard deviation in Excel. So if you want to follow along in Excel, I'll give you a minute to get your Excel set up so you can follow along with me. I have already entered the scores into the spreadsheet, and you should enter them in a similar way because you'll want them in the same cells that I have them here. Actually, I'm going to put these in the B column. There's a reason I'm putting them in the B column, so follow me here. Put your scores in the B column. Again, there's a purpose. There's a method to my madness. And then I'll give you a second to get that set up, and I'll show you how to do these calculations. The first thing to notice about the first thing to do when you're dealing with Excel is that you should always label your cells. So you see here, I have labeled this column where I put the scores. I labeled it scores. We're going to get some additional calculations down here, and I'm going to label each time I get a new calculation, I'm going to label what that cell means, because otherwise it gets very hard to keep track of what number is in what cell. So this is to help you keep track of that. And we'll just start there for now. So first we have all of our scores in here. And to get the sum of scores, click on the cell you want to put your sum in, equals sum of the scores in the column, the scores that you want to sum. So in our case, it's B2 to B7, and then enter. Now, in case you're wondering, do I really need to know how to do this in Excel? No, I don't require that you know how to do this in Excel, but I tell you what, it's worth the extra little bit of time right now to start getting comfortable with Excel, because as we get further in, you will spend exponentially more time on your work if you are not using Excel. You'll see as we get further in, we can do things in Excel where I can show you how you enter these data, a couple clicks of the buttons, you've got complex calculations done, things that if you're doing them by hand, I'm not even kidding, could take you a half an hour or more easily. So it's worth this little time investment. I know you might be a little scared of Excel. I know you probably don't use it like this, but it's a great program. It's one you're likely to have access to in the future. So you could actually do these calculations if you wanted to do some statistics for at work or in a class, which you might, or in your life. Excel is where you're probably going to do them, or if you don't have Excel, Google Docs. So it's worth it. Finally, we can get the average by, I know you're learning a lot already, but trust me here, taking the leap into Excel, it will save you time later. It's worth it. I know we're fronting that there's a lot of new things. I am absolutely sympathetic. And that's why I keep saying, call me if you have questions. Be patient with yourself. Give yourself some time to digest the information. Remember to sleep, because we had two groups of people, one who studied the same material. One group studied for 2 hours and then slept for 2 hours. The other group studied for 4 hours, and then both groups took the same test. Do you know who does better on that test? And this is research, not just my hypothesis. Research has found that people who sleep, the people who took the nap, they do better on the test. And it's because your mind solidifies these new neural connections that you're making when you're sleeping. And that's why it hurts to learn stats too. That's why it's so hard in the beginning, because your brain is literally building new neural connections you didn't have before. You're working your brain muscle hard. So you need the sleep. And the sleep will help you come to new ways of understanding it. Just sleep, Stephen, just sleep. I would rather you turn something in a day later and get the sleep, because the sleep will help you. And during your sleep, your brain will actually work out things that were troubling you before you went to sleep. So it's a really effective strategy to try to do a little bit of studying right before you go to sleep, even if you're not up late already studying, because studying stats, that is, because then you can learn some stats while you sleep. And I think we'd all agree that's the most efficient way to do it. Okay, so back to our Excel calculations. Hopefully I've sufficiently convinced you of the worthiness of Excel here, but if I haven't yet, then the ease with which we can do these calculations will certainly convince you, if not today, in the future. And in the future, when you're convinced, you'll want to be ready. So we just got the sum. Oops. We got the sum by using the simple code equals sum, and then this scores here. So we already have the sum, which we're going to use when we get the average. We remember what the average is. It's the sum of your scores, which we have in the cell B8 right now, divided by the total, the number of scores, which in this case we can see is 6. And so I just have the sum divided by 6, enter. I'm sure you might be thinking, I could do this on a calculator fast enough. Sure you could. No, you won't be able to when we have larger amounts of data, or when we have multi-step calculations where the average is just a tiny piece. Even now at the next step where we are doing the standard deviation, remember how we first needed to get our mean deviations. There's several steps here to get the standard deviation, and you first need to get the mean deviation. And again, we can do that very easily in Excel. The mean deviation is equal to X, so that's the raw score, an individual score, minus the mean, which we have down here in cell B9. And then we can copy that formula across the other cells with one little tweak to it. So since we are going to want to get the mean deviation for each of these scores separately, so this blue number will change, the red one, the average, it's going to always be the same number for each of our mean deviation calculations. So in order to tell Excel, keep this cell the same all the time, I can put a $ in front of the letter and in front of the number, and that tells Excel, always use this cell down here, B9, when we in this calculation. And I'll show you that in detail now. So you see we're on this cell and I want to copy the formula. So I can either copy in a standard way, and when I copy it, you see it doesn't copy the number, it copies the formula. So now it's getting the mean deviation of the next score, but keeping the average the same. And it's even faster to copy it by going down here to the bottom right-hand corner, and you see how you've got the white X, the white cross. Well, once it turns to a black cross, you can click and then pull down your formula, and that's telling Excel, copy this across all of the next cells I've highlighted. And if we click on them, we can see that Excel is doing just that. When you copy, I always like to click back and confirm Excel did it right. And as you can see, this looks like what we want the formulas to go through. So in sum, we first got our sum here. Just using this sum, and then our range of scores. We use that number to get our average, where we've got the sum divided by the n, which we just counted. And then we need to do our mean deviations, and it's a first step to getting the standard deviation. And when we do that, we're just taking, it's X minus the mean, or score minus the mean, right? And that's what we've done down here. Each raw score, its cell, minus the mean. And I'm just going to show you, I'm going to delete this all together because once you're in here, so I'm back in this cell, I click the equal sign, and that tells Excel, hey, and a formula is coming. And so Excel is expecting next, if I click on a cell, it's going to automatically populate in here. So I have told Excel, I want this cell to be equal to this score here in B2 minus the score that's in the mean that we calculated. And then when I want to keep the mean the same, or keep the second value the same across all the calculations, you just put the $ in front of the letter and in front of the number. And there's actually, on our Blackboard site, it's in the lab area, a link to some great help guides for Excel. Again, not random ones, but ones I've personally perused and approve of that can help you as well. And so our next step in the standard deviation is to, remember, we want to square the mean deviation. And so in keeping with my note to keep squaring or to keep track of what's in your cells, you got the mean deviation squared is what's in this column here, and that's going to be, again, equal to the number in the previous column. And then to square something in Excel, you simply use the caret up squared 2, caret 2. And if I want to copy this across these other numbers, I can just copy the formula as we did before. So now I've got all my mean deviations squared. And I know that the next step in our formula is to get the sum of these numbers. Our standard deviation. And I'm just writing out the formula here so you can see while we're doing it. And I know this is not exactly the same way they present the terminology in the book or the symbology, but don't let it confuse you. This is standard notation, basic, very basic notation. But it's what we've been talking about. We have each score minus the mean, and then we squared the scores. Next, we're going to sum them. Remember, this means sum. And to sum them, we can just do that with equals sum. Highlight our cells here, and then we have the sum. I could also drag the sum formula over from the other column here. And you can see if I click on each of these cells, it did transfer the sum. Why do the mean deviations sum to 0? Well, the mean deviations always sum to 0. It's a property of the mean deviation as a calculation. So that's something I'm expecting. And then here we have the sum. Finally, we're going to take our sum divided by n. Oops, one moment. There we go. I just colored this sum column to make it a little easier to see. And this next column I'm going to make blue, is so that we can, it's not actually doing, for our next step of the calculation. Here we have the sum of the squares, the squared deviations, and we're going to divide by n. Now this term is technically something called, that is this term here. This has a name. Its name is s squared, or, I mean, that's its symbol. It's the variance. And I'm introducing this because we're going to encounter this again later. And it's important to label your terms as you're going, so you know why I'm labeling this the variance. Oh, that's why, because the variance is a another measure of variability. And it is equal to the sum of squared scores. So we've got that numerator here. This is the squared scores. Divided by n. We know n is 6. And our variance is 25. It's just a simple step to the standard deviation now, because the standard deviation is the square root of the variance. I wouldn't worry conceptually about the variance, like what does the variance mean or things like that. I'm introducing it more to help us manage our mathematical terms, okay? So this equals, and to get a square root in Excel, it's SQRT, and then you just enter the cell that you want a square root of. You must put parentheses around both sides of it, like I have here. So you see I have parentheses around the cell, but there we have it. Our standard deviation is 5. So just to give us a quick rundown of our steps here. First, we got our sum. We used that to get an average. And then we went to the next step in computing our standard deviation, which was to get the mean deviation, or x minus x bar. And here we have it. You can see how if you accidentally are in a cell and then you click around, Excel will get confused. If you do that, just undo what you did or click out. It happens, don't fret. You can always undo what you did. That's the Control Z or Control Y, or there's these little buttons here, the arrows, so you can undo and then redo things. So here we have our mean deviation calculations for each one. And then we got the mean deviation squared. So we're here getting our x minus x bar squared. Or we could call those the squared deviations. So here we have all of those and the sum of squared deviations. Again, with our sum formula. And we have finally just two more steps. First, we get the variance, where we take our sum of squared deviations and divide by the number of scores. And then finally, for the standard deviation, we get the square root of the variance. We just okay. Any questions about this Excel piece? I guess it took a little more time than I was hoping, but we'll still go through some exercises. But let's go back because we did this mini lesson as part of another problem, which was right over here, the review exercise number 1. And we want to find the average and standard deviation of the list. Well, we have those now. The average is 50. The standard deviation was 5. Which numbers on the list are within 0.5 standard deviations of average? Within 1.5 standard deviations of average. So to get this, we need to first know what is half of a standard deviation here. Well, if our standard deviation is 5, then half of a standard deviation will be 2.5, or standard deviation divided by 2. So then we want to know what's within half a standard deviation of average. If average is 50, then that's the scores that range from 50 to, or 47.5 to 52.5. So which numbers are in that range? 40, 50, 50. These other scores are outside of that range. Then if we look at 1.5 standard deviations, then we have this half standard deviation, or 2.5, plus 1 standard deviation, which is 5. So then we have a spread of 7.5 points as our 1.5 standard deviations. And so within 1.5 standard deviations of average, we have a range of 40. .5 to 57.5, and the 1.5 standard deviations we have includes 1.5 standard deviations includes all the scores that were within half of a standard deviation plus a couple of additional scores. So now we can add to that list of scores within 42.5. Well, 41 still outside of the range. 48, 50, 50, and then 54, and also 57 because our upper limit is 57.5. Okay. And I'm going to now start breezing through some of our next exercises kind of rapidly, but if you have questions, you should interrupt me. Whitney, I'm going to keep going. Like I said, I'm going to breeze through the rest of our exercises at a fairly rapid pace. I'd say, like I told you, just a couple minutes really per problem. And then I'll continue to be here available until about 10 o'clock or so to answer the additional questions. So you're welcome to step out and come back in. You probably will want to, at some point, watch the exercises that we're going over. But in terms of this next piece, doing the remaining 11 exercises, we're going to do those fast. So they'll take a small fraction of the time that first one took because we were doing I was teaching you how to do the computations. So next up, we have we're going to, just one moment. Come on. What's that, you big baby? You're staying. Sorry, folks, if I don't let that cat out, then we won't be doing, all we'll be doing is just listening to meows for the next several minutes. All right. So now we have two lists that have the same average of 50. Which one has the smaller standard deviation and why? Let's not do any computations, okay? So I'm looking at this first one, and the first thing I'm going to look at is the range of scores here. So the range of scores looks like it goes from 25 to 75. And what's the range on this next one? A low of 25 to, again, a high of 75. So the range isn't going to give it away, but I can see there's a difference in the number of scores. So the data sets are the same for the first 7 scores. And then this second list has 3 additional scores that are all the same. They're 50. I bet 50 is 50 is the average. So since these data sets are the same, but this one only has some additional numbers that are at the average, we know these are going to be the same. They have the same standard deviation. Oh, wait, excuse me. They have the same average. Of course they do. The standard deviation sorry about that. I got ahead of myself. These keep this spread the same, but because it changes the n, okay. Sorry, here I got some issues with my pen. Okay, so because it doesn't change the spread of the range, but because the n is bigger in this smaller in the number 2 is going to be smaller. Because when you have a larger number in the denominator, you end up with a smaller overall ratio at the end. Okay, let's look at our next list. same scenario. The first 6, 7 scores are the same. And then all of a sudden we have another score that is one outlier at the top and one outlier at the bottom. So this is the opposite. We have the same data, but when we add in these scores that pull the tails way out, we end up with a bigger numerator. So then the smaller standard deviation is going to be this first list that has a smaller range of scores. So here with this second list, so just in summary, we can use the range effectively because these scores range from 25 to 75, but these ones range from 1 to 99. That pretty much tells me that this is going to be a larger standard deviation because I know these scores have a bigger deviation in the whole range of scores. All right. Next up, another list of numbers. Without doing any math, thank goodness, guess whether the average is around 1, 5, or 10. Okay. Well, looking at this list, I can see that there's numbers above and below 5. The average can't be 1 because there's numbers way above 1. It also can't be 10 because then we'd have to have mostly numbers that are 10 or numbers above 10 even. So the average has got to be around 5. And then on our second part, we're going to guess whether the standard deviation is around 1, 3, or 6. This is a little trickier, but if we just think about this again, if our mean is about 5 and a standard deviation is 1, then we would have, remember, we would want to have the whole distribution within 6 standard deviations from the mean. So since the average is 5, if the standard deviation was 1, then above and below 1 standard deviation would be equal to a range of 4 to 6, and plus or minus 3 standard deviations, which remember should have the whole distribution in it, we would have 2 to 8. But we already know we have numbers below 2 and above 8, so it can't be 1. If we look on the other side of this, could it be 6? Well, using this same logic, clearly not, because if even just if the standard deviation was 6, even that first standard deviation, plus or minus 1, we would have a range of scores from -1 to 11. And so that's not possible. That doesn't fit. So our standard deviation must be around 3. And that more or less fits. I know we don't quite, it doesn't quite work out in terms of the 6 standard deviations for the whole range, but it's the only answer that makes any sense, so it's got to be 3. Now we have persons aged 25 or over in the US. Would the average or the median be higher for income or for years of schooling? First, let's think about income. To do this one, we want to visualize what does this data set look like that is average income. Well, we kind of already know what income is distributed like in the US, right? We know that there's lots of people who make some, relatively or extremely less money than this small number of people who make a ton more money than the rest of us. And it's been this way for a long time. This situation is discussed in your book. And so that's how where you're supposed to come to that information. But again, if you're in a question like this where you're thinking, well, how do I find this information? You're not clear. You can always reach out to me. Text or call me. I'm happy to say, oh, yeah, here's what we're talking. Here's why. So if this is our distribution for income, then we know since this is a scenario where we have a positive skew, the mean is always pulled towards the skew. So would the average or the median be higher for income? Well, the median would be about here. And the mean, well, that's a little high for the mean, but it's on the positive side of the mean. So income, the mean is higher. Lucky I'm not in teaching you spelling. Then if we look at years of schooling, we can, we're going to have a similar effect, but in the other direction. So again, we have our x-axis, and for years of schooling, most people get we're going to have most people we're going to have most people topping out with education. I'm sorry, this is hard to, I've got a mix up in my tablet here and it's hard to draw these. All right, here we go. So what we're going to see with years of schooling is that most people top out here around college, but then the skew is going to go in this direction. Pretend this is a smooth curve here. And so this is the opposite type of skew, where the mean is, the skew is in the negative direction, and the mean is always going to be pulled toward the skew. So the mean is going to be smaller. Okay. And now we're going to look at those blood pressures. I know you want to go out there. Go over there. I don't know if you could hear her growling to go out, but it had to happen. So here we are. Now we're looking at men aged 18 to 24 in Haynes and their systolic blood pressure. Average was 116 millimeters, and the standard deviation was 11. And now let's look at each of these blood pressures and decide if they're high, low, or about average. So our range for one standard deviation above and below the mean would be 105 to 30. Oh, it's not 37. 137, of course. And right? No, 127. Duh. You can tell I normally do my math in a program. So we would expect scores in this range to be about average. This is about average, 115. 120 is still pretty close to average, right? 210, that's very high. And 80, that's very low. And that's how I made that decision. And I know I'm going through these quickly. Remember, if you have a question about one of these items as I'm going through it, please stop and ask me. That's absolutely fine to do. But in the absence of questions, I'm going to just keep going through these quickly. So now we have sketches of histograms for 3 lists. And you can see already what the general topic is going to be here. We have 3 histograms, 1 symmetrical, 2 skewed. So that's certainly going to factor in. In scrambled order, the averages are 40, 50, and 60. Match the histograms with the averages. Okay, well, we can see that, and it's always good to take your low-hanging fruit first where you can. So we have one with an average of 50. It's quite clear that this one with the average of 50 is number 2. And then we have a diagram down here with an average that's above the mean, or that's 60, above 50. Well, that's got to be diagram number I. And finally, we have one with a mean of 40 down here. So this is probably 40, 50, 60. Sorry about the last noisy cat. There's nothing I can do about her. She'll chill out in a minute. She can't go outside and she's mad. Match the histogram with the description. The median is less than the average. Well, we've been practicing this all night. When is the median less than the average? Well, when the average is more than the mean, or more than the median. The average is always pulled in the direction of the tail. So the median is less than the average when we have a positive skew, like we do here. Okay, we have a positive skew down here, or on the right, and that means that our mean is going to be higher than the median, or another way to think about it, the median is less than the average. So that one is going to be number 3. The median is about equal to the average. This scenario happens when we have a symmetrical distribution like we do here. Oh my gosh. Hey, can you chill out back there? You, chill. Okay. And we have finally a third scenario where the median is bigger than the average. And that's scenario 1 here. This happens in a negative skew. And here we have it. The median, the mean is always going to be pulled towards the skew, like here. And so that's number 1. Now, is the standard deviation of histogram 3 around 5, 15, or 50? All right, well, again, we're just trying to use some logic about these to come to these answers. So we'll look at histogram 3. Could the standard deviation be 50? No, because that's a huge standard deviation, and we couldn't possibly get 6 standard deviations of the size of 50 in this data set here, right? If the standard deviation was 5, that seems like it'd be awfully small, because 5 times 6 would be 30, and the scores clearly have a range bigger than 30 points. 15 seems to be just about right. This 15 times 6 is 90, and that's about right. As you can see that 100 points, these are converging on the tails, and remember, these are smooth. So this last, I even overestimated it. So you could say, we can easily say that all the scores range within 90 points approximately. And certainly from among these options, 15 is the one to go with. And finally, true or false. The SD for histogram 1 is a lot smaller than that for histogram 3. Well, this is false. Histogram 1 and histogram 3 are mirror images of each other, so their standard deviations will also be approximately the same. And that would be a sufficient answer for this. It says true or false and explain. You just say, which one is this true or false? Well, it's false because these are mirror images, so their standard deviations will also be mirror images, or something approximately that. I'm really only looking for brief descriptions here when you're asked to explain. Keep it brief. Next up, we have a study on college students that found that the men had an average weight of about 66 kilograms and a standard deviation of 9 kilograms. The women had an average weight of 55 kilograms and a standard deviation of 9. I'm going to keep track of our men and women up here in the top, since I can't quite use my left-hand side strategy. Notice I put this, my mean, and then I put a little m next to it. That's to remind me that it's the mean for men. And then we have a standard deviation for men of 9 kilograms. Over here we have women. It was 55. Whereas the standard deviation is the same as it is for men. It's 9. Oh, now we need to find the averages and standard deviations in pounds. So in order to convert these numbers, we want to take our we're going to take our kilograms and then multiply by our conversion factor. If 1 kilogram is equal to 2.2 pounds, we can just take our number of kilograms and multiply by 2.2. How am I going to do that? Well, like I do everything else in Excel. It'll only take us a minute though, because we already know the basics of doing this, doing calculations in Excel. And sometimes I'll just use Excel because it's quicker to show you things. So we're not going to do it in great detail right now. I'm just going to do this for our calculation purposes. So we have our scores here. We have weight. We have we have an average and a standard deviation. Men. And then we have women. We already know these are 6, 9, and 55 and 9. These are our kilograms. And then I'm going to want to duplicate this to get these, convert these numbers to pounds. I'm going to end up making another table down here. Pound, SD pound. Is going to equal this score, our score, times the conversion factor is 22. 22 or 2.2 pounds for each kilogram. And the conversion factor is the same whether we're doing it for the average or the standard deviation, and these two. So you can see, to get this, I still took the average, and then just multiplied by the conversion factor or the standard deviation. and multiply by the conversion factor. Okay, so back into our problem. Oops. I'll bring it back in a minute. We found the averages and standard deviations in pounds. I'm not going to write them in. We saw them right here in case you wanted to reference that back. I can copy this over if I want. I just highlighted the area, the cells, and I clicked Control Copy. And if I want to paste it in here, or if I was doing this homework and I wanted to paste this into my Word file, I could just copy it like that and then paste it, which you can do with a drop down or Control V. And you can see here is the data. It's a little different to manipulate it in Word. It's actually a little bit easier, but just copy and paste over like that. Easy peasy. Okay. And just roughly, what percentage of the men weighed between 57 kilograms and 75 kilograms? Well, 57 is one standard deviation below the mean, and 75 is one standard deviation above the mean. How did I figure that out? Well, I subtracted 9. I took 66 minus 9, and then I took 66 plus 9. And so what percentage of men are between that area? We already know it's going to be 68% because there's always 68% of the population is within one standard deviation above and below the mean. It's just the rule. That's how it works. There we go. Remember that number. You need to know it. If you took the men and women together, what would the standard deviation of their weights be? Excuse me. If you took the men and women together, would the SD of their weights be smaller than 9 kilograms, just about 9 kilograms, or bigger than? It'd be just about 9 kilograms. How do I know that? Because they both the men and the women have a, oh, actually, it would be not just about 9. So common misconception. I fell into the trap too myself for a second there. Even though their standard deviations are both 9, so the standard deviations are both groups are the same. If we took them together, then the standard deviation would be bigger than 9 because the total spread of the data would be bigger. Okay. Back to the Haynes 5 sample, the average height of boys was 137 centimeters at age 9, 151 at age 11. At 11, the average height of all the children was 151. Okay, on average, are boys taller than girls at age 11? No, because how do I know that? Well, if at age 11, what are the average height of boys? The average height of boys at age 11 was 151 centimeters. Then if we look at all children together, their average height is also 151 centimeters. So they are not taller than the girls because the girls and boys clearly have the same average. Guess the average height of the 10-year-old boys. We can do this by just finding the difference between the age 9 height and the age 11 height and dividing that in half. Another way to do that would be to just get the average of 100 of these two heights, because 10 is the average of 9 and 11. Our average height is going to be at 10 years old, it's going to be that same thing, 137 plus 151 divided by 2. for an average height of 144 centimeters. Now on problem 9, we have an investigator with a computer file showing family incomes for 1,000 subjects in a study. And